Euler also give a theorem to determine whether a graph is planar or not. So let's see that theorem. So here, suppose G is a connected planar simple graph. So if G is a connected planar simple graph with, so number of edges is E and number of vertices denoted by V, and suppose R is the number of regions we get on this planar representation. So if this is the case, then the number of regions is equal to number of edges minus number of vertices plus 2. Okay, so by this formula, we can easily identify whether a graph is a planar graph or connected planar simple graph. If we see that any graph does not satisfy this following formula, so we can easily determine that graph is not a planar graph. So let's see how many regions we will be able to find for these following graphs. First example, we will see total number of vertices. There are 7 vertices. Okay, so this is 1, 2, 3, 4, 5, 6, 7. And if we compute number of edges in this graph, we will see there are 11 edges. So we can see there are 6 regions in this planar graph, and we will see whether this is satisfied. So R is equal to E minus V plus 2. So we can see E is equal to 11 minus 7 plus 2. Number of regions is equal to 6, and we will also see that by doing this algebra we will get also 6. So that means it is satisfiable. Now next one is how many regions are there. So definitely we can see this is R1, R2, R3, and there is an infinite regions are 4. We also need to see whether equation satisfy for this graph. So we can see number of vertex in this graph is 4. Number of edges in this graph is equal to 6. And we can also see that 6 minus 4 plus 2 is equal to 4, and there is exactly 4 regions, right? Now next one, how many regions are there? Total number of vertex here is 8, and number of edges in this graph is equal to 12. So number of regions in this planar graph is equal to 12 minus 8 plus 2, that is equal to 6. Okay, so we can try to check whether it is 6 or not. So R1, R2, R3, R4, R5, and infinite regions are 6. Now from this theorem there are 3 corollaries we will get. So let's check the first corollary. The first corollary states that if G is a connected planar simple graph with E edges and V vertices, so here E means the number of edges and V means the number of vertices of that graph, where V is greater than or is equal to 3, then E should be less than or equal to 3V minus 6. Okay, based on this corollary, we can say that K5 is not a planar graph. So here it is mentioned that K5 is a non-planar graph using corollary 1. So this is also important to mention based on which corollary we are making this decision. We can try to find whether it is true or not. We know that for K5, number of vertex is equal to 5, right? And number of edges is equal to 10. Now if this is the case, so what we will get in here, 3 times V minus 6, we will get 3 times 5 minus 6, and we will get 9. Is 10 less than or equal to 9? No, right? So that means since for this K5, this equation does not satisfy, that is why we can say that K5 is not a planar graph. Okay, now there is another corollary. It states that if G is a connected planar simple graph, then G has a vertex of degree not exceeding 5. So you can also use that one, and you will see that based on this corollary 2, we can find out whether a graph is a planar or not. Now let's see another corollary. Third corollary states that If there is a connected planar simple graph has E edges and V vertices where V is greater than or is equal to 3, another condition that no circuit of length 3 is also exists, then number of edges is less than or equal to 2 times V minus 4. So that means if there is a planar graph and there is no circuit of length 3, then that planar graph has number of edges that is less than or equal to 2 times V minus 4. Based on this corollary, we can also prove that K33 is not a planar graph. We have seen that previously, like how we proved that K33 is not a planar graph. So we tried to put these vertices into different regions and we were unable to do that without edge crossing. Here is by using this corollary, we can also get this conclusion that K33 is not a planar graph. We can also try to check this one. For K33, we know that total number of vertices is equal to 6. We know that if K, M, N, number of vertices m plus n. We can also find the number of edges by doing this multiplication m and n. So therefore we see number of edges is equal to 9. So what we will get 2 times V is 6 minus 4. So we will get 8, right? Now if we put this equation, we will get 9 is less than or equal to 8. Is this true? The answer is no. Okay, since this is contradict to this equation, therefore we can say that K33 is not a planar graph based on corollary 3. You see that using corollary 3 we found that K33 is not a planar graph, but if you use corollary 1, maybe you will see that this is a planar graph. So this is very important to mention based on which corollary you are thinking this graph is not a planar graph or this graph is a planar graph. There is another theorem that will help us to determine whether a graph is planar or not planar. So this theorem is widely applied in many cases. So this theorem is called Kuretsky theorem. Theorem states that a graph is non-planar, that means a graph is not planar, if and only if it contains a subgraph homeomorphic to K33 or K5, or we can also say in plain word that a graph has a subgraph of K33 or K5. So what is homeomorphic? You can go back to see the definition. It states that if G1 and G2, if there are two graphs, they are called homeomorphic if they can be obtained from the same graph by a sequence of elementary subdivision. Okay, so what is elementary subdivision? So I also give the definition of elementary subdivision, like you can remove some edge and then you can add some vertices. So in a short, we can just say that if a graph contains K33 or K5 subgraph, that graph is not a planar graph. Let's see an example. Now, if we look at this graph G, so we remove some edges and vertex by doing elementary subdivision. So what we can see by removing vertices and edges, we actually get K5. So in this graph G, K5 is a subgraph of this graph G, and that is why this graph is not a planar graph.